Okay, so today's lesson is 1.6 and it is on complex numbers. So our objective today is to solve quadratic equations with complex solutions and to perform operations with complex numbers. Apply the complex numbers to fractal geometry. Okay, so complex numbers are numbers that come in the standard form a plus bi. So what that means is that your real number will always come first when you're writing these in standard form, and your imaginary number will always come second. So that is the standard form of a complex number. So similar to when we were doing standard form of linear equations or quadratic equations, we had a specific order in which we needed to write all the terms. Same thing applies for this. Okay, so what exactly are imaginary numbers or complex numbers? So imaginary numbers are defined to handle the problem of taking even roots of negative numbers. So we were doing some solving quadratic equations using roots the other day, and when we got to something like at the end where we maybe had the square root of 9, then we would say that the solution was positive or negative 3. But if we had gotten something like, square root of negative 9, then we would have said no real solution because there's no number times itself that would equal a negative 9. So imaginary numbers now will solve that problem. So anytime you have the square root of a negative, or negative 1 technically, it can come out as an I, or an imaginary number. So let's try a couple examples so you can kind of see how that would work. So basically, if you remember our product property with the radicals, any radical can be broken down into two radicals that are factors of that original. So if I have a negative, I'm just simply going to break it up into the number itself. So in this case, negative 16 would be broken down into 16 and then also a negative 1. Now, square root of 16, that's a positive number. We can get our positive and negative 4 from that. And then the square root of negative 1, if we look up here, is equal to I, which represents an imaginary number. So our solution here is positive or negative for I. So if we were to do that again for the next problem, this would be 49 and negative 1. Square root of 49 would be positive or negative 7, and the square root of negative 1 would come out as an I. So it would look like that. Now when we get to the next two examples, these are not perfect squares, so we can break them down the way we were using either the factor tree or just perfect squares. So if I were to break down a 12, for instance, and I used 4 and 3, and then a 2 and 2 for my 4, I would get positive or negative 2 radical 3. Now I also have this I that's going to be multiplied by that. Now the only catch is when you have an I like this, after a radical, it actually needs to go in front of the radical sign. So your answer should look like this, plus or minus 2I radical 3. And that would be the appropriate way to write that answer. So going on to the next one, we have 24 and negative 1. So you're just separating out that negative until the end. 24, you just break it down as you normally would. So we end up with plus or minus 2 radical 6. And then because the negative 1 inside the radical is an I, that I just goes in front of the radical along with that plus or minus 2. Okay, so now the second portion here is an I squared. So if you take an I squared, that is actually the square root of negative 1 times another square root of negative 1, which then the square roots cancel each other out and you're just left with a negative 1. So anytime you have an I squared, it can be rewritten as a negative 1, which will come in handy at times because then to get rid of that variable, it's essentially like a variable that I squared in a problem, you can substitute it with the negative 1 and then further simplify. Now, before we get into other problems, let's just kind of look and see how these different i's work out with various exponents. So for example, let's say you have an I to the 7th. Well, what does that really mean, right? So if I have I to the 7th, that means I really have I squared. How many I squareds? 2, 3, and then I have just this extra single I here. So I squared times I squared times I squared times I. Remember, you add exponents, that would be I to the 7th. Now, the reason I did that is so that you could see each of these I squares is really equal to a negative 1. So because this was an odd exponent here, we ended up having 3i squareds, but we still had that leftover I at the end. So you're still going to have an I on your answer here, but -1 times -1 times -1 would just be -1. So my answer is -I, or -1i. Now the next one is an even number. So it's going to take 4i squareds to get me that I to the 8th power. And each of these I squareds is really equal to -1. Now this one's different than the last one because one, since it's an even exponent, there's no leftover there. There's no remainder where I have an I at the end. So there's no I in my answer. And then the other thing is, since I have 2 -1s here and then 2 -1s here, or 4 of them all together, they're all going to cancel and I'm just left with the answer 1. Now let's see how that varies from the next problem. So the next problem, I have I to the 9th. So I have 4i squareds, just like I did for I to the 8th, but then I have one additional I at the end for that extra 9th one. Okay, so notice this is an odd exponent here. So my first 4i squareds are all going to be -1s, but then I still have that extra little I left over at the end, which tells me I'm going to have an I on my answer, right? Now, because I have 4 -1s, every 2 would cancel out, so I'm just going to be left with a 1. So my answer here would just be positive I. All right, and then finally, the last one here, I to the 10th, I'm going to have 5i squares here, because that will give me a total of 10 of the i's, which is what I had in the original. So each of these I squares is really equal to -1. So I really have 5 -1s being multiplied together, which, since there's an odd amount of them, that would be -1. So as you can see, if you're writing it all out and then replacing each I squared as -1, you can kind of figure out what the solutions are. However, sometimes you might get a problem where it's like, I to the 243rd power, or something kind of crazy like that. So if that happens, just a shorter way to do this, obviously, so you can kind of notice, like, first of all, every I squared is a pair of i's. So the first thing that you would want to do is take how many i's you have, in this case 7, divided by 2. Now 2 goes into 7 3 times evenly, but you do have that remainder of 1 there. Anytime you have a remainder, you know your answer is going to have an I on it. Now this tells me that I have 3 -1s. Any odd amount of -1s is going to mean my answer is still negative, and that remainder tells me that I have an I there as well, so it's -I. Now if I were to do the next problem, 8 divided by 2 is 4, and there's no remainder. So the fact that there's no remainder there, because that was an even number, there's no I in my answer, there's no leftover I's. And because 8 divides by 2 evenly and I get an even number, that means I have 4 -1s and an even amount of negatives. They'll all cancel out. So I'm just left with +1. For the next one, 9 divided by 2 gives me 4 remainder 1. Since I have a remainder, that means I'm going to have that I left over. So there will be an I in my answer. But 9 divided by 2 gave me 4, which is a even amount of negatives. So all the negatives will cancel. And then the last one, 10 divided by 2 is 5. There is no remainder, so I don't have to worry about an I in my answer. But there's an odd number. There's 5 -1s, so that will give me a negative answer. So you can kind of revert back to these notes if you need help figuring out some of those values of I to like a very large exponent. Okay, so using these to solve quadratics with complex solutions. So the first thing we want to do is get the x squared by itself, just like we would for any other equation. Since there's only one variable, that x squared, we're going to get it by itself. So now we have x squared equals -16. Once the variable is isolated, because it's a squared, to undo that exponent, we need to square root it. So that then gives us x equals positive or negative 16, breaks down into a 4, but because we have the negative on my 16, I also need to put that I on my answer, as I showed you earlier in this page. Okay, number 2, also going to get an x squared by itself here by dividing both sides by -2. That gives me x squared equals -25. square root both sides. X equals positive or negative, and this time it would be 5i since 25 is a perfect square. Don't have to worry about breaking it down or doing the factor tree or anything like that. Okay, and then number 3, my x squared is here, so I'm going to subtract my 26. So 2x squared equals negative 36. X squared equals negative 18. All right, and then x will equal positive or negative. Now, the negative 18, I'm going to break up over here into a negative 1 and an 18. My 18 is going to break down into 9 and 2 and 3 and 3. So this is going to be 3 on the outside and a radical 2, but then my I is going to go on the outside with the 3. So my final answer should look up. All right, so let's see if I can scroll down a little bit here. All right, so now we're going to move on to graphing complex numbers. So when we have a complex plane, basically how it kind of converts over to a graph is we know the standard form is a plus bi, and that's kind of just going, you're going to take those coefficients and you're going to make them an ordered pair. So basically your real number is going to be your x value, and your imaginary number or coefficient there is going to be your y value. So as long as you have this in standard form over here, as long as they're not switched up on you or trying to confuse you in any way and they're in standard form, it should be pretty straightforward to see the ordered pair. So my real number here is 2, my imaginary number is 3, so 2 comma 3 would be the point that I would graph for A on the complex plane. For B, I have negative 3 for my real number, and this is really just a 1 for my imaginary number. So negative 3 and 1 is that point there. Okay, for C, I don't have a real number, so that's going to be 0, and then 2 is going to be my imaginary number, so that's C. For point D, I have negative 2 and negative 4. For point E, there is no real number, so that would be 0, and then that would be a negative 1 there with the negative I. Oops, sometimes my... so that is 0, negative 1. And then finally, this last one here, 4 and negative 2, and that would be point F. All right, so now we're going to do a little bit of operations with these complex numbers. So to add or subtract complex numbers, it's simply combining like terms, okay? The only catch is if you have an I squared, you can replace that with a negative 1 and then maybe simplify a little bit further. So your imaginary numbers are like terms, those can be added or subtracted. Your real numbers would be like terms, those can be added or subtracted. And you have to make sure that your final answer is in that standard form of A plus BI. So the key here is a lot of times people make a mistake and they try to distribute or FOIL, but if there's a plus or minus in between the two sets of parentheses, there's no multiplying or FOILing or distributing, it's just combining like terms. So in this case, I have a negative 1 and a positive 3 here. So if I combine those, I will get 2. And then if I want to combine my i's, my imaginary numbers, I have 2i and 3i, so that would give me a 5i. So that would be my combining like terms, so to speak, addition problem there. Now for number 2, before you get into what we just did there, you have a subtraction, and you have to make sure you're subtracting both of those terms there in the next parenthesis. So it's really 2 minus 3i minus 3 plus 7i because we're subtracting that negative. Now you can go ahead and combine the like terms. So my real numbers, 2 minus 3, gives me negative 1. And then my imaginary numbers of negative 3 and positive 7 give me that plus 4i there at the end. All right, let's try a couple more. So now the next one, we have a plus, and then here we have a minus and a minus. So let's see how those kind of work out. So when we just have addition signs, I don't have to worry about distributing anything because everything's going to stay the same. So I'm simply just going to look for my like terms. So I'm going to start out with my regular numbers. So I have a 3 and a 2, so that's going to give me 5. And then when I go to do my real numbers, I have a 2i and a 1i, which gives me 3i minus 3i. So then they all end up canceling, and my answer is just 5. Okay, number 4. So I have this 4 in the front, but then I'm subtracting a negative 2, which really means I'm adding 2. Then I'm subtracting this 8i. Then I'm subtracting a 1, and then I'm subtracting a negative 2, which means I'm really adding that 2i. Then I want to combine my like terms. So 4 and 2 is 6, minus 1 is 5. And then I look at my imaginary numbers here, and I have negative 8i and positive 2i, which would give me negative 6i. All right. All right, so we're going to do 2 more. These are just a little bit longer because we have this time plus and minuses in these problems. So again, anywhere there's a minus, that is going to be distributed. So I'm just going to copy this over without my parentheses and then make this a minus 5 and a plus 9i since I'm subtracting that negative. Then I'm going to combine my like terms. So as far as the i's are concerned, negative 3 plus 9 would be 6i. And then for my constants here, or my real numbers, 8 minus 5 is 3. And notice that I'm going to put it in the front because that is the standard form. Okay, and then the final addition and subtraction problem here, I have 30 minus I minus 18 minus 6i plus 30i. So my numbers first, I have 30 and minus 18, which is going to give me 12. And then when I go to my imaginary numbers, I have negative 7 plus 30, which is going to give me a positive 23i. And again, it's in standard form. All right, so moving down. So now we're going to go into complex numbers with multiplication of complex numbers. Now the difference here is you have to just look at your placement of those parentheses. So notice here that my parentheses do not have a plus or minus in front of them. And here the two parentheses are next to each other. That is when you do your foiling or distributing. If there's an addition or subtraction sign like the last set of problems, that's just combining like that, okay? So now at this point, we are going to distribute this 2i to each other term here in the parentheses. And it's just like if there was x's or y's or some other variable, you do the same process with the multiplication. So 2i times 3 would be 6i. 2i times 4i, you would get 8i squared. Now, prior to doing the imaginary numbers, if you had a problem like that, you would be done at this point. Except now you have to remember I squared really equals negative 1. So because we have an I squared in our answer, we're not finished. So what I need to do now is I need to replace the I squared with a negative 1. And every time you do that, basically what's going to happen is it's going to switch the signs. Instead of it being plus 8, now it's going to be minus 8. And we're basically done, except it does have to be in standard form. Okay, that's your A plus BI. So my negative 8 needs to come first, and then my positive 6i needs to come second. And notice the sign in front of the number always stays in front of that number. All right, so let's take a look at the next one. So 3i times 9 would be 27i, and 3i times negative I would be negative 3i squared. Now, the I squared is going to be replaced with that negative 1, which then makes that 3 plus 3. And now we just have to put our answer in standard form, which would be 3 plus 27i. All right, let's try the next one. Okay, this time we're getting into the distributing or the FOILing. So 6 times 4 is 24, and 6 times negative 3i would be negative 18i. Then we take the negative 5i and distribute that, so we get negative 20i and positive 15i squared. These two in the middle are both just regular i's, so they're going to combine. We're combining those like terms. And then over here, my I squared is replaced with that negative 1, which is then going to make that a minus 15. And then, of course, these two like terms, the 24 minus 15, can be combined to give me a 9. And I have 9 minus 38i for my answer. Okay, let's take a look at number 4. Negative 1 times 3 is negative 3. Negative 1 times negative 6i is positive 6i plus 12i minus 24i squared. The middle two are both i's, so those are like terms that can be combined. So I get 18i in the middle, and then minus 24 times that negative 1 is going to make my 24 become positive. Now when I combine those like terms, I can get my final answer, which is 21 plus 18i. Again, it's in standard form with the real number coming first and the imaginary number coming second. All right, a couple more now. Distributing still. So when I look at number 5, I have 3 times 2, which is 6. And now I distribute my 3 to the negative 2i, which is negative 6i. Then when I distribute the 3i, I get positive 6i, and then I get negative 6i squared. So the two single i's in the middle are going to cancel since I have a positive and a negative of the same thing. And then I have minus 6 times negative 1, which is going to become, of course, positive 6, and then that just equals 12. Okay. Number 6, 4 times 4 is 16. 4 times 9i is positive 36i. Then we have a negative 36i, so those are going to cancel. And then negative 36i squared. So be careful because a lot of people forget to do the squared. And then that messes up your answer because the I squared obviously changes to a negative 1, which then makes that 36 become positive, and then we add those together. Oh wait, I wrote 36 by accident. It should have been 81. My apologies. 81, 81, 81. Okay, so now we are at 97 for our final answer. Okay, so let's take a look at number 7. We got 2 more multiplication problems here. Okay, so for number 7, we have negative 6i squared minus 18i minus 4i minus 12. Now this time the I squared is still going to be negative 1. These two i's in the middle are going to combine to give you negative 22i. Negative 6 times negative 1 becomes positive 6. And then I combine those and I end up with negative 6 minus 22i. Right. And then one more. Now, one common mistake for this next problem is that people want to distribute the exponent, but you don't distribute exponents to binomials. Only a monomial can you really do that. So you actually have to write it twice because this basically is saying 1 plus 8i times itself, and then you have to do the distributing. So 1 times 1 is 1, plus 8i, plus another 8i, plus 64i squared. Now you might remember this looks a little familiar from when we were doing the factoring a couple sections ago because this would be a difference of, perfect square trinomial. Except that now that we have the I squared, then that little extra piece is going to come into play. So this becomes 1 plus 16i minus 64. And then when you combine those like terms, you get negative 63 plus 16i. Okay, so moving on. So we're now going to go on to dividing complex numbers. So dividing complex numbers, it's a little bit similar to when we were doing the radicals last week and we had to rationalize the denominator. So similar to the radicals, you're not allowed to leave a radical in the denominator. And if you had one on the bottom, you'd have to get rid of it, right? Same thing applies with the imaginary numbers. So for example, I'm going to put an example that's not here. Let's say you had something like, 2 plus, let's see, radical 3 over radical 6. Okay, I'm just making this up. Okay, you can't leave this radical 6 on the bottom, right? So you would have to multiply both the top by radical 6 and the bottom by radical 6, right? So the bottom would now just be 6, and the top, you would have to distribute that. So you would actually get, let's see if I can erase this so I can write it a little bit neater. Oops. Okay, so radical 6 times 2 would be 2 radical 6, and then radical 6 times 3 would be radical 18, which then, let's see, 2 radical 6 plus, I think that's 2 radical 3 over 6, and then these would each reduce. So you get radical 6 plus radical 3 over 3. Okay, so hopefully you kind of get the idea. But essentially what's going to happen is if you have a radical in the bottom, you'd have to multiply top and the bottom by that radical to get rid of the radical in the bottom. You can have them in the top, it's not the bottom. Same kind of process here. So in order to get it to cancel, when we did the radicals, you multiplied it by itself and they canceled the radical out, right? Well, when you're dealing with complex numbers, you have to multiply by what's called a conjugate. And a conjugate is pretty much the same real number and the same imaginary number, but the opposite sign in the middle. So if you remember when we did that factoring with the difference of two squares and we had the two different binomials with the opposite signs, that middle section canceled when we multiplied. Well, that's why this works, because then when we do FOIL them or distribute them together, the i's cancel. The I squared gets replaced with -1, and we no longer have imaginary numbers in our denominator. So for this one here, the conjugates, a plus bi and a minus 3i would be considered complex conjugates. I think that has an extra letter or something in there. Okay, and so then this one here, 6 plus 3i, and then it would be 6 minus 3i. So just the middle number the middle sign has to be different. Doesn't matter what sign you have on the beginning or the end, it's just that middle sign that has to be different, okay? So write the expression as a complex number in standard form. So what we're going to do for these, they're kind of, I'll be honest, a little annoying. So you end up with you have a binomial on the top and the bottom here. Okay, so what we're going to do is we need to multiply by the conjugate of the denominator. So since this is 1 plus I, I'm going to do 1 minus I like that. And then the same thing on the top. So now this is where it gets annoying because now you have to FOIL the top and FOIL the bottom. Now, I'm always going to do the bottom first because it should cancel stuff out. And if it doesn't, then we might have done something wrong. So 1 times 1 is 1. 1 times -I would be -I. Then I'm going to get a positive I. And then -I squared. So you see these two canceled. And now on the bottom, I'm just left with 1 minus -1, which of course becomes 1 plus 1, which of course becomes 2. All right. So now I'm done with the bottom. I'm now going to go up to the top. So 2 times 1 is 2, minus 2i, minus 7i, plus 7i squared. Now on the top, these two in the middle are going to condense or combine to give me minus 9i. And then I have plus 7 times -1, which of course is -7. And then 2 minus 7 will be -5. So I have -5 minus 9i over 2. Now, if the 5 and the 9 were both divisible by 2, I could simplify it, but they're both odd numbers and they're not divisible by 2. Okay, so let's try this with the next one. So first things first, you want to figure out what is your conjugate. So my conjugate is going to be -1 plus 2i. Notice I did not change the sign on the 1, just the middle sign. Same thing is going to get multiplied to the top. Okay, so now I'm going to do my bottom. So I'm multiplying here, -1 times -1, which is +1, minus 2i, and then I'm going to get a plus 2i because the two negatives multiply together, we get a positive, and then minus 4i squared. So be careful. That's usually when the mistake happens. People write like 4i or they write 2i squared, stuff like that. Okay, so now just simplifying that to make sure it works. These two are both opposite sign. They cancel. So I have 1 minus 4 times -1 on the bottom. That, of course, gives me 1 plus 4, which, of course, simplifies to 5. So now I'm going to do the top, which should work out a little bit, won't cancel out as much. 3 times -1 is -3 plus 6i minus 11i plus 22i squared. So I have -3. The two middle terms combined, they're like terms, so -5i. And then I have plus 22 times -1, which of course is going to be -22. And then -3 minus 22 is -25. Okay, so now this is an example of where both of these numerators are divisible by 5. So I can actually simplify this because 25 divided by 5 is just 5. And 5 divided by 5 is just 1. So my simplified answer would be -5 minus I. All right, so we're going to do a couple more here just to practice. This is where most of the mistakes happen. It's just being very careful. So first things first, my conjugate here is 1 plus 2i, multiply by the same thing on the top and the bottom. So on the bottom, I'm hoping most of this will cancel. So I have a plus 2i and a minus 2i, which of course are going to cancel. And then I have minus 4i squared. And then continuing that, I have 1 minus 4 times -1, which is really 1 plus 4, which is really 5. Then on the top, I get 5 plus 10i plus 3i plus 6i squared. So 5, my two like terms in the middle, give me a 13i in the middle, plus 6 times -1. So 5 plus 13i minus 6, and of course 5 minus 6 is -1. All right, let's see. All right, and then we're going to do another conjugate here. So again, my conjugate is 5 minus 2i, 5 minus 2i. Let's go down. Okay, so on the bottom, I'm going to get 25 minus 10i and plus 10i, which are going to cancel. And then minus 4i squared. A lot of 4i squareds on here. Then on the top, we have 10 minus 4i plus 25i minus 10i squared. Be careful with those squares. Don't miss them. Okay, so now on the bottom, I have 25. My 10i's cancel, minus 4 and times -1. Of course, that's going to make it a plus 4, and then that's going to make it a 29. In the numerator, I have plus 21i in the middle, And then I have minus 10 times negative 1, which of course is plus 10, which is going to give me a 20 in the numerator plus 21i, and that's over 29, and that's my answer for that one. All right, so very tedious, kind of long, kind of annoying, but that's how it works. Okay, and then the final thing for this section is the absolute value of complex numbers. And if you can just remember the formula, which you guys are lucky because you will have access to your notes, it's very simple process. Essentially, you're taking your real number and you're squaring it, your imaginary number and you're squaring it, you're adding them together, and then you're square rooting. Now, because we're squaring each of these, it doesn't even matter if you put a negative on or not. If you forget it, you remember it, you put it there, you don't put it there. Because when you square a number, whether it's negative or positive, you're going to get a positive, right? So you should always be adding together two positives and then square rooting that. So basically, if you take a look, you want your real number, which this first one, this would be your A, right? And this would be your B. So all you're going to do is 3 squared plus 4 squared inside the radical. So of course that's 9 plus 16, which is 25, and then you're just going to get 5. Now remember, it's absolute value, so we're not concerned about getting the positive and the negative here because we're just going to do the absolute value. So it's the distance, so we're just worried about the positive answer. So that would mean that this number is 5 units away from the origin. Okay, so number 2. So again, my A is this 2 or negative 2. My B is this 5. Again, you don't need the negatives or the positives. It doesn't really matter which one you put because when you square it, you're going to get a positive anyway. So it's 4 plus 25, which equals the square root of 29. Now that is not something that you can simplify. You could only get a decimal answer. So it's radical 29 units away from the origin of the complex plane or whatever decimal value that is. It's like 5 point something. Okay, now the next one, don't let it trip you up. The A here would be 0 and the B would be that 6 or that negative 6. So when you go ahead and put those in, you got 0 squared plus 6 squared. Obviously, you don't really need the 0, right? So if it's not there, you don't even need to put it. This just equals the square root of 36, which of course is just 6. Okay, the next one, you got your A and your B. So 2 squared plus 3 squared is 4 plus 9, which equals 13. And square root of 13 is as far as you can go. It doesn't simplify. It doesn't break down. You can't use a factor tree. It's a prime number. Okay, and this one here, again, you just have that B value. So all you have to do is square root that. Now this one does break down. So your answer would be 2 radical 2. All right, and we got one more here. So this is our A and this is our B. So 9 squared plus 6 squared, 81 plus 36. So that's like 117, I believe. And again, that's a prime. It does not break down or simplify, so that's as far as you can go. And that's it for our notes on imaginary and complex numbers. The historical note is there at the bottom if you'd like to read that. I did discuss it in class. And that's it. Have a great rest of your day.